Thank you for the introduction. I'll be talking about theoretical methodologies towards practical quantum machine learning. Basically, at Osaka University, I'm researching the quantum machine learning and how we are doing the research. A more recent overview of the research is something that I'd like to talk about. First of all, the machine learning, as you are well aware. If there is a given data set, the model that can approximate that, or the function f is being solved. That is the purpose of machine learning. In case of a neural network, as you can see, there's 100 numbers and given, and then in the neural network, from 0 to 9, which one is correct? That is the function that you constitute, and that is the basic aim of machine learning. And there are many outcomes that are coming out, like image recognition. So there is a huge computation capability of machine learning. And what is the benefit of the machine learning from quantum computers? I think that would be something that is naturally asked by quantum computer researchers. And if you would like to learn this, the approach that has been thought about is a quantum neural network, is among others. You use a quantum circuit, and in the quantum circuit, the parameters will be embedded, and you put in the input data, and the output that is coming out would constitute the model that I mentioned, where you can predict the combination of numbers, and you can use the quantum circuit to do that. And another approach is quantum kernel methods. In a quantum status, you encode a data, and the similarity between the quantum statuses or internal product is used to do machine learning. So those are the two approaches in the near term or in the near future can be used for machine learning. So these are something that is considered to be promising. Now, so there are several approaches that are proposed, and in some quantum circuits, you cannot simulate them with classic computers. So if you would like to do exactly the same with classic computers, that would be impossible. But for example, image recognition in other practical applications, are there any benefits from quantum machine learning? We don't know yet. And what has been said is that for the data that is generated from quantum computers, or the data that can only be handled by quantum computer, there might be some meaning that you can find from quantum machine learning. So far, the tasks that have been solved by classic computers could be cannot be performed with a better performance. Nobody has said that, and so it's going to be difficult to achieve that. So what the quantum type data is something that you can handle with the quantum machine learning. That is something that we see some promise. So in the horizontal axis, the status of quantum, like psi, and then the vertical axis is model, and you receive psi, and then something meaningful, like characteristics of the psi, could be found, and that is one possibility. And other things that can be considered is quantum neural networks. So how does it work, and how can you ensure performance? You have to know that first to know which application that you can use this for. And so for these issues, we have made some researches, and I'd like to share some of those research activities with you today. First of all, for the quantum learning of quantum data, In order to do quantum machine learning, you have to handle quantum data and you have to machine learn the quantum data. So what do we need to do? One research that we have done is to generate quantum data first and foremost. So how you can generate the quantum data. And that is what we have done first. So I think this has been mentioned in other presentations, but VQE algorithm is heavily researched in NISQ. And for example, when you generate quantum data, then VQE and other approaches will be used to generate quantum data. That is something that you can consider. So what was the VQE? There is Hamiltonian given, and you have to find the lowest level energy, and the quantum computer will be adjusted in a variance manner. And that is what we call UC. And with this fine-tuning on the computer, you would optimize the parameter theta. So that is what VQE is about. And so VQE could be used for generation of quantum data. So if you would like to learn what the VQE has done, is it really practical? That is the first question that you have to ask. So optimization is now difficult. So it takes too much time to actually converge that because the number of calls is too many. For example, in a molecular system, for example, if you would like try to do VQE, whether VQE itself can work is questionable. And the table at the bottom is from 2021 from the paper. For example, if you try to work on ammonia molecule, if you look at the cost column for molecular ammonia, AWS bracket could be used, and in order to make the VQE work, then it will cost you 100 million. And so it is not practical, so you have to do something about VQE. So what we have come up with is this. So classically, the optimization loop should be completed on the classic computers. That is the approach that we try to take. Then, how can we do that? In a quantum computer, you cannot simulate that on a classic computer. You cannot complete the optimization of a quantum circuit on a classical computer. But if the circuit is shallow enough, like you see on the right, then even classic computers can make it work. So that is the characteristic. And why is that? So as you can see on the right, the circuit in the right can be used, and you try to measure the 3 qubits. Then if there is a total 109 qubits, you only have to simulate the orange part. So that means that only 8 qubits should be simulated, and that is easy enough for classical computers. So for shallow circuits, you don't have to use quantum computers. You can only use classic computers to make it work. But what is important in this approach is that the local quantity, like 3 qubit output, is the only thing that you would like to know. Then that could work. But if you like to know the information about the overall, then non-local physical quantity is something that you would like to know. Then even if it is shallow circuit, you cannot do that. If there is 109, and you have to do simulation on 109 qubits if you like to know the whole information. And as an example, the machine, as an example of machine learning, the inner product between quantum states or similarity degree. So even in the shallow circuit, it is impossible to simulate this on classical computers. So how does it work? So on the classical computers, you you close the VKE circuits or loops, and then generate output. And as you can see at the bottom, after all the loops are over, you measure the inner product between the quantum states on quantum computer. So for the VKE, everything was done in classical computers, so optimization can be easy enough. And however, you cannot calculate the inner product, so you have to borrow the power of a quantum computer just for that part of deriving inner product. So this is numerical verifications. It is quite technical, so I'll be very brief. As a Hamiltonian, there is a cluster model that is used, and we run the simulation. And then, once you do this, with the VKE, the inner product between the states, the framework of optimization of classical computers, as you can see here, based on the value of inner product, you can do the classification, and you are successful in phase classification via clustering. So in a sense, you can take a good advantage of classical computers and then borrow the power of a quantum computer toward the end. Then the bottleneck of optimization or quantum data optimization in the classical computers can be solved. Now, a totally different topic. There's quantum data that has been generated through the approach that I just mentioned. Once you have that, the phase classification via clustering was done. So using that quantum data, you would like to do not just clustering, but something more. And one of them is visualization of quantum data. And that is what we have done. So often, in the classical machine learning context, the visualization method that is often used is TSNE, T-stochastic neighbor embedding. So there is this approach, and using this approach, TSNE, if there are handwritten letters, as you can see on the right, the one is which cluster, and you can visualize that with this tool, TSNE. So in the TSNE, there is a variant of TSNE, a bit different from the original TSNE, and what we call parametric TSNE. What does this do? If there is an input x given, then you put that input in f function, and the outcome of this function, if you put x in function fx, then you have to make sure that visualization is good, and you put the input, then you can get one data point, and that is what we call parametric TSNE. Using this method, for example, those handwritten letters can be classified like this. Then what would happen if you use a quantum computer for this? First of all, as I said, you can use quantum neural network in a high dimensional space, like images, and vector information can be converted into lower dimension, and that is f theta function. And this can be built with a quantum neural network. That's what we figured, and this is a proposal that we came up with. And on the left top, there's quantum data. The data generation method that I mentioned can be used for quantum data, and then this will be put into quantum data computer, and then parametric quantum circuit will be run and do the measurement, and based on the measurement value, the visualization data can be obtained. Now, this is what we call TSNE, and this has been converted into the quantum community, and how you can optimize the parameter theta, and that's where TSNE is coming in. And what is the cost function? The data conversion, the similarity. So the inner product of quantum states and the quantum data status in low-dimensional space should be similar to each other as much as possible. And by optimizing the theta, the green, orange, and blue can be clustered like the one that you see in this diagram. And that is the approach that we are proposing. Now, we did not use the actual machine, but this was a numerical verification done, like annealing like Hamiltonian. So this is a bit different from the data generation method that I just mentioned. So Hamiltonian dynamics was used to generate this quantum data, and quantum bit visualization was done. So using Hamiltonian, we generated the status, and the status has been visualized. In order to generate two classes, the Jij part of the Hamiltonian, there are two classes taken, or plus or minus, a positive or negative. So there are two classes of data generated, and we try visualizing them to see what happens. And when you do the clustering, the orange and blue points are clustered in a low-dimensional space. So intuitively, this status is similar to this, that it can be sensed. So visualization is something that is quite helpful to human beings because they can be understood intuitively. So last but not least, there is another topic. The quantum neural network is what I mentioned, but how you can optimize quantum neural network, that is something that we need to consider as well. So that is what we have done, and I'd like to share that with you as a last topic. And the clue to this neural network, or this research, is that the neural network that is not quantum data, what is happening? So what is well known is that wide neural networks can be trained with small parameter variations. That was already known. And you can widen the width of neural network, then you can increase the accuracy of the training, and that is well known. So what is the process of that training? The parameter change is very small. The output of the training, because of the small parameter variations, can be linearly approximated. So based on that, when you look at the equation in the middle, you see that the model, the f theta x, the gradient vector is linear regressed, and this is equivalent to that linear regression, and that is what we call neural tangent kernel. And this actually represents the training of neural network, and this was well discussed. Then what happens in quantum data? The similar thing happened, and if you deepen the circuit, then the parameter change becomes smaller. And in the neural tangent kernel, the quantum version of neural tangent kernel could be defined. So as you can see in the middle equation, you take the inner product of the quantum circuit, then you can actually characterize the very deep training process of quantum circuit. So there are many challenges, like how quantum network is working, and when there is a quantum network, what should we do? There are several challenges remaining, but in Osaka University and around the world, the research is ongoing, and many people are coming up with new ideas to solve this. So this field is still immature, but I hope you can closely watch what is going to happen. And thank you for the attention.